So yesterday I started reviewing some aspects of F theory.
Let me just tell Sujay about your talk. He's here. Probably doesn't. Yeah. You continue.
Okay. So F theory is about 7 branes which appear as singularities in elliptic fibrations, and the classification of codimension 1 singularities in elliptic fibrations was done by Kodaira a long time back, and this is the result of his classification. So various types of singularities have these names. There are 2 infinite families called Ik and Ik star, and the other ones are just some exceptional cases. The monodromy is the monodromy in the SL2Z. And here these 3 columns describe the order of vanishing of the functions f, g, and delta at the location of the singularity. So remember, we are studying a Weierstrass equation of the form and delta is.
So these are singularities which preserve some supersymmetry.
There's no supersymmetry. It's just elliptic fibrations with codimension 1 singularities.
Right. But if we take string theory on this, for example, if we have just these 7 branes, it preserves.
Yeah, but there will be restrictions on the base as well. So the thing in our situation, we want 6-dimensional theories, and so we want an Calabi-Yau threefold, an elliptically fibered one.
Like this, with one of these.
So it will have many of these singularities. They will be codimension 1, and then they will intersect at codimension 2 singularities.
Because if I naively take something from Ik, 1k, and from 1k star,
Yes.
these would correspond to D7 branes and anti-D7 branes.
No, there are no anti-D7 branes here.
Oh, these are all just.
Yes.
So what constrains these forms of singularities? Is it the fact that the resulting manifold you want it to be scalar? Because a priori, if I don't care about a torus vibration or real torus vibration on 2 dimensions, presumably I could do that for any monodromy, right?
Right.
That's probably part of your question.
Like is the C1 of the resulting manifold, C1 of the canonical bundle of the resulting space, C1, maybe of this.
No, this twofold is not a Calabi.
Not 2-4, whatever the total space of
No,
this
but
vibration.
this thing is describing torus vibration on a plane. So it's a 4-dimensional.
The
Otherwise, what
F1G can be functions of the full 10-dimension coordinates.
no,
That's
but
what it is.
monodromy is about just in a plane, right? So it's describing D7 singularity, certain way singularity. So you can take the rest to be flat. Just
But it can be in different 2 planes.
but for simplicity, we can just take everything happening to be in a plane.
Right. So okay. So the total space here is 4 dimension, 4 here. And if we just look at each singularity.
So maybe I don't know how many conjugacy classes are there for SL2Z. Are there more than these? Yeah, so I don't know the basis. What is the what this classification is based on?
But these all have. Is it some? It's not all K3, right? The total space. K3, probably K3 for some of one.
So presumably you also
Local analysis. So local K. I'm just saying something like C2 mod set K. Would be probably.
so I think you also want that your singularity should not be very bad. It should be something of orbifold type. It must have resolution in terms of some. So when you resolve the singularity, you should get some extra p1s intersecting in some fashion. It should not be a very bad singularity. So these are what are called minimal singularities. And there are non-minimal ones as well, which have order of vanishing of f, g, and delta bigger than for these numbers.
The minimal.
These are the minimal ones.
Minimality condition that in this classification. This will mean you can polarize them and get any similarity. I mean, I don't know.
I see. Yeah, maybe. Yeah, there are other singularities which are called non-minimal ones. And I think that string theory is not well defined on those singularities. But I never understand the argument. There are lots of arguments why you should not consider those singularities. And yeah. Okay, so here by order of vanishing of f, g, and delta, I just mean that when you approach the singularity, f will behave like z to the order of vanishing of f, and so on. And because these are singularities, deltas have to vanish anyway. And in the last column, I have associated an algebra to all of these singularities. So this one is pretty obvious. For ik, these corresponded to k d7 branes, so it should have SUK on it. I star k corresponds to, so this is k d7s, and this one is O7 minus along with k plus 4 d7s. So now from this, there is an after the orientifolding action on this, you obtain SO2k plus 8 gauge algebra. For the other ones, you have to use the duality to M theory to argue that these are the gauge algebras which should be living on these 7 branes.
So this action of ik star, the monotony, it's the same on tau, right? As ik and ik star have the same monotony on tau.
On tau, yes. But yeah.
But if that would be action on tau, then
But there is a Z2 reflection in the geometry as well from here. This reflects A and B cycles. So
That center of SL2 center.
it behaves like D7 up to
This model by
up to a Z2 transformation.
and how did the 4 come? Like, if you don't want to give the rest.
The
It's easy
4,
to see how the 4 comes in this.
I mean, you just look at, the RR charges. So the RR charge of O7 plane is minus 4. So it gives you K RR charge. Okay, notice that there is no O7 plus in this list. And so I will talk about O7 plus later. Okay, so let me give arguments why these gauge algebra should be these ones. So how do you determine them? You use the duality between M theory and F theory.
Sorry, I mean, is this the state? But related to the question I asked last time, if we put these singularities
Mhm.
and try to solve the supergravity equations, would you then, ignoring validity, would you then get solutions that preserve, would all of these preserve the same supersymmetry as the D7 branch preserves?
Right. The question of supersymmetry can just be answered by general arguments, right? Is that the compactification of you're compactifying type 2b on some base.
Let's forget the base. Suppose I just take this, I take a solution in which I've got a point and I have my dilaton doing something,
I see.
axion doing something around that. I don't care what happens at infinity.
Mm-hmm.
Okay, so I've got a solution that has great deal of symmetry.
Mm-hmm.
Okay, it preserves 8-dimensional Lorentz invariance. So it's effectively just non-trivial in 2 dimensions.
Right.
I try to find a supergravity solution
Mm-hmm.
that winds in these 2 directions, and I demand that it preserves the same. Will all of these do all of these locally preserve the same supersymmetry as the D7?
I mean, they do, yes.
Like, no, ik star, there's an O7 along with the D7.
Yeah, this is on top of it. So there is the same supersymmetry.
Same supercharges.
Same supercharges, yes.
Yeah. Okay, so I see. And then of course you can put multiple ones there. So maybe that's the point. And these are the only supersymmetric solutions with the supersymmetric? I mean, maybe there's some statement about geometry, but we don't care. Because there isn't really a geometry. There's no real 12-dimensional geometry. This is just some statement about how dilettante axiom goes. So the question about whether it's allowed or not should be a question about physics.
Right.
But I think this classification is about minimality because you can bring them together and winding will add up, right? And that will not be in this table.
But
No, so there is an SL2Z action involved in this, right? So I don't understand how you will use supergravity.
I'm going to forget about the validity of supergravity. The problem with the SL2Z is that somewhere the coupling becomes large. I use supergravity and allow gluing. Once I go around, I allow multi-valued fields glued by SL2Z.
Okay.
And so I think that's a reasonable prescription. Because I forget about validity. Usually supergravity doesn't care, things like analysis about supersymmetry don't care about validity. But let's see about Abhijit's question. Can't I take any two monodromies and create all of them? Suppose I take a basis of two monodromies. Let's say monodromy of S of the flip and monodromy of T and S.
Yeah, TNS do create it, but not necessarily the other stuff, right?
The TNS would be sufficient.
Would be sufficient to create everything. And don't we have TNS somewhere here?
I 1
1 and 3.
Sorry, which one?
1 and 3.
Right. So I think it has to do with the fact that your singularity should be of orbifold type.
Why should I care? Singularities of orbifold.
I mean, you want, to read off this gauge algebra, right? You want it to.
After doing some duality, this thinking of this as a torus is total fiction at this point.
Right. It's
So
totally.
whether it can be blown up or not, there's no real 12-dimensional manifold.
No, but if you go to M theory, this torus becomes real.
Right. So after you go to do some view with it.
Right.
But I think the statement that these are minimal still is correct, right? It's the fact that if you have this type of order vanishing, order of vanishing and so on, you cannot quite split it further and make it a smaller.
That means relatively prime.
A notion of relatively prime.
I'm just trying to understand your minimum. You're saying that you cannot?
I mean, you can think of bringing together two singularities and make a bigger singularity, right? And also the opposite. Then these are the prime ones where you cannot do the opposite.
But for K, if we just follow that, the 1K, then the subscript 1 should be enough to do it. K does it seems at least.
If you do what?
So if I take 1, 1 and 1, 1 next to each other, then we should
It becomes 1, 2.
1, 2 from this kind of understanding. But each one of them seems to be a different minimum.
Okay.
Okay.
Right. So it says somehow the statement is about the fact that those 7 branes won't have nice coupling to the bulk. You were looking for solutions of the bulk theory, but
Yeah.
the 7 brane itself won't be well defined. Okay. Right. So to introduce the F theory M theory duality, let me focus on the example of some D7s first. So suppose you have k D7s and you wrap them along a circle of radius r. Then you can do a T duality to go to type 2a, where you have a k D6s orthogonal to this, to a circle of radius 1 over r. And now you just lift this to M theory. And you obtain an elliptic fibration, you obtain an extra circle, So D6s are going to be lifted to a top nut singularity. So the new M theory circle is going to vanish, is going to pinch to nothing at the location of the D6 branes, and you have this extra circle. So you get an elliptic fibration with IK singularity, which is precisely this. So in this singularity, one of the circle pinches off at the location of the singularity. And in this map, the area of the torus at a generic point is equal to 1 over R, and the complex structure of this torus is equal to tau. So if you want to describe k d7s in flat space, then the area of the fiber becomes 0. Okay. So similarly, we believe that F theory on some general manifold X times S1 will be dual to M theory on X. So here X is an elliptically fibered Calabi-Yau manifold, and you put it on a circle which is not a part of this manifold, on some extra circle. Okay, and this will geometrize the extra directions that you had here. Okay, so the way you determine the algebra now is to resolve the singularity on the M theory side. When you resolve the singularity, you obtain some. So for example, you can obtain a configuration like this: a bunch of P1s which intersect in some fashion. So each of these whenever they are touching each other in my drawings, it will always mean that they intersect each other transversally with the intersection number 1. And now, so in M theory, you have the RR3 form, sorry, not the M theory 3 form, which can reduce on these P1s to give you some gauge fields. Which live in the Cartan subalgebra of the Lie algebra that I am writing over there. So in this case, they will be in the Cartan subalgebra of SO8. And you also have M2 branes. So you can wrap M2 branes on these. There will be some massive particles in the theory. There will be W bosons for these gauge fields. And combining them, you see that when you turn off the resolution, you obtain a gauge theory with gauge algebra G.
H is the Cartan.
H is the Cartan.
Can you say again, sorry, I missed where do the 2 cycles come from?
Which thing?
The 2 cycles.
So one of them was already there, here, and one of them came from the left.
That's from the resolution. I think he's talking about the 3 months.
These 2 cycles?
Yeah.
Ah, okay. So you just resolve the singularity. So in the case of IK, you will obtain something like a fine quiver, something like this. Okay.
So once you resolve it, this elliptic fibration structure is lost.
No, it's still an elliptic fibration. It's just that I mean the geometry is not the most singular one anymore. So the singular fiber has this form rather than the singular form, which was this one. So this was I4 singularity. So originally it looked like this, and now you just change the fiber to this. The singular fiber becomes this when you resolve it. So nothing changes, the Weierstrass equation is the same, the complex structure is the same. This is the extra Kähler parameter. So if you want to describe it, it will be in terms of the Kähler, some Kähler moduli of the fibration, not the complex structure moduli. Weierstrass equation captures the complex structure moduli. This was a very special point in the Kähler moduli space, and now I'm on a generic point.
How would you get an intersection form like that, which is not not
That comes from I4 star, from I0 star singularity.
So it's part of this, right?
Yeah.
But then it's not quite a pinched.
Right, so it looks like with a sphere with a singular point. That's the fiber, and which resolves to this. Maybe 3 singular points. I'm not sure about, but these are the resolved forms. Yeah, I think like this. Then the middle one comes out of it, and the other ones.
No, but you started with an elliptic fibration, right?
Yes.
Not quite a sphere with some.
But the singular fiber could have any kind of. The singular fiber could be a rational curve as well.
The singular fiber would just be a torus with pinched cycle.
That's the usual case.
Okay.
But if you have a monodromy like this, you obtain spheres. You obtain rational curves with singularities. Okay. Now let me say some words about O7 plus. So can I erase this? So if you have O7 plus along with, and on top of it you place K minus 4 D7s, then it has the same RR charge as O7 minus with a K plus 4 D7s, and both of them involve the same Z2 action on the geometry. So this means that they have the same monodromy. And so both of them should be described by the IK star singularity as far as the Weierstrass equation is concerned. But still, the two situations can be different as far as the geometry is concerned. They might be at different points in the Kähler moduli space. However, so Witten showed that this is not the case. So they have same geometry. And so in F theory, they look exactly the same. They both correspond to IK star singularity, which is not resolved. So the question is, right, so what distinguishes them? In F theory. And this is still not known.
Algebra, you also say is the same, so it will give the same for both.
No, the algebra is different because this will be SP.
Right. So when you say what distinguishes them, in theory you mean some geometric.
Yeah, some geometric way to distinguish them.
Because this resolution pattern will be different for these two because you either get SO or SP. And the degree diagrams are different for those.
No, the resolution is also exactly the same. So it's just that, I mean, there are no sometimes there are no resolutions. For instance, if you put K equal to 4 here, so I4 star, it starts from I4 star, right? K greater than or equal to 4. So if you put K equal to 4, there are, you see, So if you're classifying codimension 1 singularities, resolutions and deformations are the same things, and deformations correspond to moving d7s of the surface of O7. So you see that the I4 star singularity cannot be deformed because there are no d7s, but this I4 star singularity can be fully deformed. So there, so
Isn't that already something distinguishing this?
sorry.
That's the fact that is distinguishing them, right? Then
Yeah, so one of them is frozen, you cannot deform it, and one of them is not frozen.
no, let's say
That's a
start
property.
with K equals say let's say I6 star or something. Then you can resolve both.
I6 star can go up to I4 star, and I6 star of the other kind can go to IZ, just completely can be made completely smooth, deformed to a smooth thing. So this one, if you want, is IK star with a hat on it, which tells you that this one is frozen, partially frozen, and this one can be completely deformed. So this is one of the properties, and you have to, whenever you say you have an IK star singularity, you have to tell me, is it of the partially frozen kind or is it of the usual kind, unfrozen kind? And people always assume that all of these IK star singularities are unfrozen.
What if you work your way backwards from the resolved? So you're saying when you resolve, you should get an SP group in the first case, and in this case, you
No,
also
when they're not resolved, it's SP. When this is not resolved, it is SO. When this is not resolved, this is SP.
I thought you are getting this algebra by resolving and then thinking.
Then you get U1s, right? You get U1s with some W
Yeah,
bosons.
right. So now if you do that, and then you get a U1 for S,
No, so yeah, so the duality to M theory itself is modified in this case. So in the correct duality to M theory, in M theory you know how to distinguish between these two cases. It's just that, okay, so let me tell you how the duality is modified. Right, so MF duality for this. So in M theory this becomes again an IK star fibration, and at IK, so let me consider K equal to 4. I4 star fibration, which has, so I4 star carries a D8 singularity because it was carrying, right, SO2K plus SO16. So in the M theory realization of IK star hat, you don't have a D8 singularity, but rather this D8 is broken down to D4 plus D4. So you have a sphere, here you have a D4 singularity, and at another point you have another D4 singularity, a line of these things. Right, okay, sorry, I should. Okay, so you have a D4 and a D4. And now there are some 3 spheres around them in the full geometry, and on both of these S3s you have a fractional flux for the M theory 3 form. So this is the fact which is making it frozen in M theory, that you cannot break it because you have this flux. And any broken singularity cannot carry any fractional flux to match up this. Okay. And also you cannot combine them to a single D8 singularity. So the simple story that F theory on some manifold compactified on S1 is dual to M theory on the same manifold is not true when you have O7 plus planes. And the full duality is not known.
So these diagrams that you draw, these M-theory diagrams,
Yes.
sorry, I don't understand them. So what kind of manifold are you drawing? What dimensionality?
So it's real dimension 4.
Real dimension 4. And so then you're drawing, what
So this is the singular fiber. I have a plane on which I have an elliptic fibration, and at some point I have a singularity, and over the singular point the fiber degenerates into something like this, into a P1 with two singular points.
Maybe this is the same thing that related to what Abhijit, less sophisticated version of what Abhijit was asking. But so everywhere else, what I have is just some torus.
Yes.
Now, I can't understand what this means. So this, P1 with, so it's just a sphere with two singularities.
Yes.
I see. And you're telling us about the nature of this.
So yeah, these are codimension 4 singularities.
Fine.
Right.
And these are like orbifold singularities?
Yes, yes. They are D4 kind. D4 orbifold.
I see. And you said that, and one example of that was this D7, or just plain D7 brane.
Yes.
Because you trivialized to D6 brane.
Yes.
And then you got the usual kind of
Top
singularity
nut.
at the top.
Yes.
I see. Okay, fine.
Okay.
So in the intersection between two spheres, you have one of the circles of the torus shrinking in the downward case. Right? When you do the intersection diagram for the spheres,
Yes.
one of the circles describing one of the P1s was the circle of your torus, right?
Mm-hmm.
And the intersection of two spheres, that circle shrinks to 0.
Yes.
So then the torus becomes one of these degenerate torus at each of those intersections.
Right. So there was some shrinking like this, right, to start with.
Yeah, even that diagram I don't understand. What is that? So just one of the cycles of the torus
Yes.
is
It has.
shrinking to 0.
It's shrinking such that
And
I
this
mean.
is the C2 mod ZK point in
So-
dominant.
It's shrinking such that you have a monodromy of this type,
Yes.
And that
and this one can be resolved to k plus 1 P1s intersecting each other.
so it's in dominant it's like separating the K fold singularity into K one fold singularity.
Yes, precisely that thing.
And so when you split this into K P1s,
Yes.
it's those P1s which extend between the one fold singularities. That's the idea.
Yes.
So you're distributing that pinching points into K points.
So top nut is just the local version of this local.
Right.
You just zoom into this singularity, then you get the top nut
And if we resolve that, that point will split
into k P1s. But actually there were k plus 1. It's just that you have zoomed in.
Right. So the
Yeah.
K plus 1 will form the affine.
Yes, will form the fine one.
Suppose we had just one D7 brane.
Yes.
Then also there's some shrinking,
Yes.
and that would be what P diagram in that case?
It will just be 1d7. Right. So you don't. It will just be this. It will. It's in that case you don't have a singularity, right? You don't have a. It's just the usual top nut.
It's just the usual type nut.
Yes.
But you don't think of that as singular because one of the circles is shrinking to 0 at the point of.
The fiber is singular, but there is no singularity where there is some physical
The
fields.
full manifold is not singular.
Yes. So there is no resolution or something.
Fine.
So from this counting, it will just be U1 gauge theory.
SU1, nothing. There won't be anything. There will be a decoupled U1
Right. Okay.
in all of these things.
And this resolution, and if you had now two, I'm sorry to
Yes.
stop, but suppose you have two of these, two D7 branes, then what is your diagram, please?
Then you will have this one, right? So just two things intersecting at 2 points, right? Two P1s intersecting at 2 points.
And is this diagram meant to denote a smooth space?
Yeah, this one is smooth.
Is
No,
smooth. So is
each
that-
one has a top nut singularity.
Basically, you've separated the two branes.
Yes, precisely the same.
Okay, fine.
Then the W boson is
Fine.
Okay. So right. So in today's talk,
Also see that this should be something like a top nut from the boundary point of view, right? You have a torus vibration on a let's say a disk with some singularity, but at infinity it's a vibration on a circle with monodromy, and that is probably the length space, which is the boundary.
Okay. You just, I mean, you know the resolution of these singularities,
Right,
and they just
if
form
it's-
this Dinkin diagrams.
Right, but if we also think of the way he was talking about as a length space, then it's C2 mod some finite group subgroup of SU2.
Okay.
And there is an ADE classification for those,
Uh-huh.
resulting in these finite Dinkin diagrams.
Yes.
And
So
that
that one, those singularities are just obtained by zooming in at these singularities.
for
Yes.
the ones which you have to do that.
Yes.
But for
So
those
there are
who-
these. So I'm just saying that the AD singularities are embedded into elliptic fibrations in this case.
So it's not a coincidence that we get only those algebras. It has this M theory.
Yes, they are the same things.
Except for the O7 plus, which you explained.
Also, it's physically different, but mathematically it's the same object.
But because of this, we can't think of them as ADE singularities.
No, they are. It's just that they're protected by a fractional flux.
So they're protected, so it
They cannot be resolved. Physically, they cannot be resolved. So you have to impose this extra condition on them. Yes. Okay, so in today's talk, I want to focus on classification of six-dimensional SCFTs and latest string theories when you have no O7 plus anywhere in your geometry. So in this case, there are many nice because of the duality with M theory. There are many nice features, and the classification can be completed. Okay, so right. So we want 1,0 supersymmetry in 6 dimension. So we compactify F theory on an elliptically fibered Calabi-Yau threefold. And we assume that this Calabi-Yau threefold, let me call it X. X is non-compact. And this has the consequence that gravity decouples from the 6-dimensional theory. One way to argue this is the following, that the 6-dimensional Planck length will be governed by the volume of the base of the Calabi-Yau threefold times the 10-dimensional Planck length. And since the volume is going to infinity, the 6-dimensional Planck length goes to infinity. Sorry, 6-dimensional Planck mass goes to infinity. Okay. So now a key role is played by 2 cycles in the base of the elliptic fibration. So let me pick a basis for these 2 cycles. So let dA be one of these bases, and I'm choosing a representative dA in each of the. So dAs are a basis for the cohomology, second cohomology of the base, and the dAs are some representatives of these cohomology classes. Okay, then I can write my. So type 2b theory has a 4 form. I can write it as, in terms of this basis, let me decompose it in this basis, where delta 2 dA is the delta function supported on these, sorry, these were homology cycles, on these 2 cycles dA. Okay, the fact that X is Calabi-Yau lets you prove that all of these B2As are actually anti-self-dual. So what it means is that their field strengths are anti-self-dual. So this for
Statement about the base being
Oh, sorry, it's being a.
Positive definite intersection form, something like that?
No, no, I think it's a consequence of the fact that this basis can be obtained from a basis of harmonic forms, harmonic two forms, and harmonic two forms are either the Kähler form or the primitive 1,1 forms. The primitive ones are anti-self dual, and the Kähler form decouples because you have a non-compact base. So it's some technical argument. Okay. So now you have D3s which can wrap these two cycles dA, and in the sixth dimension they will produce for you strings. Some linearly independent. These are the linearly independent strings in your sixth dimensional theory. Right. Okay. So in the 10-dimensional theory, you have a coupling of the following form for B4. From this, you can obtain a coupling for the effective six-dimensional coupling for the for these six-dimensional two forms, and you obtain a matrix MAB times the coupling for this. For these two forms, and as before, if you supersymmetrize it, you obtain the kinetic term for the tensor multiplet scalars. And so from this, you see that you obtain some restrictions on MAB. So what is this MAB first of all, right? This MAB is supposed to be some form, the intersection number of these DAs, right? So this is intersection form. Okay. So first assume that MAB is indefinite, this intersection form. Then you see that you don't have a good six-dimensional theory. So you have unstable tensor branch. The next case you can consider is that MAB is positive semi-definite. So you allow some zero eigenvalues for MAB. And this would imply that some of the tensor multiplets are non-dynamical because they will have a zero kinetic term. And the other tensor multiplets would be good dynamical tensor multiplets, stable tensor multiplets. As a consequence, the waves for these tensor multiplets are going to be mass parameters for your theory. And so you expect that these theories are actually little string theories because they have mass parameters. And notice that till now there is no restriction on how many mass parameters you have.
Why is the phi fixed when there is no kinetic term?
I mean, if you choose a wave, you cannot. It doesn't fluctuate, right? It's background.
Well, you could. You are doing a path integral on it, right? Why is it?
No, you're not doing a path integral. It's non-dynamical. It's a background field. It's precisely a background field.
Maybe Abhijit's asking if there's a potential for it.
No.
Flat potential.
Yeah, there are 8 superchargers, so there's no potential.
So like spontaneous symmetry break. You get some wave and it just stays. There's no
What does that have to do with the mass? Kinetic term being there or not there? I mean,
argument holds for
Yeah.
any of these files.
Why can't you give a wave to the other files as well?
You can, but then it will fluctuate. It's a modulus of your theory.
That's right. But the expectation value
At infinity,
at infinity is fixed.
Yes, yes. But I'm saying that these ones cannot even fluctuate. These are not fields in your theory. They're not dynamical
I
fields.
would say they fluctuate a lot, right? There is no separation coming from the kinetic term.
I mean, there is no equation of motion for them, right?
I mean, in the path integral, all slow varying contributions are not dominated.
I mean,
It's
So-
not like they're Lagrange multipliers. Do they appear at all in the action?
right? They act as a Lagrange multipliers for. No. Right. So the
When kinetic term is not there, that means fields fluctuate a lot.
Right. But a situation where kinetic term is not there is when you put a Lagrange multiplier.
Sure. Yeah.
So it
But
imposes some
that's very
identity.
specific.
So whatever it couples to, if it couples linearly, will just be set to 0 exactly. As you say, as a field.
right. So this is going to. So this appears in a coupling of the form. If there was a gauge theory there, assuming there was a gauge theory coupled to it, then there will be trace f s star f. So you're setting to 0 this thing, the kinetic term for the gauge field. So its Yang-Mills coupling is going to be a parameter.
I mean, if it is a Lagrange multiplier, then why would it even be? Why would you even give the value? You just integrate it.
Right. It just sets that trace to 0.
Yeah.
But maybe there's a quadratic, it appears this way. Is there also a quadratic piece?
No, this is the only quadratic piece. I mean, so if there are 0 eigenvalues, there is no kinetic term for them, for those things.
So why is there a path integral over these?
Well, just like any other field.
But these don't descend from M theory, right? It's just a supersymmetric.
So they come from this.
So that's the supersymmetric completion of that.
I mean, so all I'm saying is this, right? I'm just saying that they will appear in a term like this,
Right.
and if it's not dynamical, it's just some wave, it's just some number, it's just a parameter of your theory.
No, but it,
Unless there is an integral over that.
but he's asking why is it not dynamic? He's saying that
So-
take the equation of motion of that. That says equation of motion says trace.
So phi only appeared in this term and in this term.
So now let's
right.
look at the equation of motion for phi.
No. Just look at the Lagrangian.
I'm looking at this.
So here there won't be any phi over here, right? And the phi appears here.
Right.
Just like a Lagrange multiplier.
Yeah. So this is not a field. I'm not integrating over it in the path integral.
Why not?
Why not?
I mean,
Even if there is no kinetic term, why not integrate over it?
Was the corresponding B a field?
so in the string theory setup, it will turn out that it's frozen completely. This thing is. Yeah, the corresponding B will also not appear in the path because of MAB.
What is the origin of this phi A from the type 2B?
Yeah, so it's living in this multiplet and the multiplet of before.
Before. So is it
So I'm just repeating what Abhijit saying. You know, normally the coefficient of kinetic term is 1 over g squared. Coefficient being 0 is g squared being infinity. So it's infinitely strongly coupled.
Mm-hmm.
not very weakly found.
Right.
So you need some other argument for not integrating over it.
I mean, suppose I was to write a mass term for this, then this being 0 would imply an infinite mass term. This is just the mass, right? If you normalize your phi by this, you obtain a mass. It changes the mass, right?
Right, right.
So this will just tell you that it's a massive field.
Okay, but is there so if there was a phi square term, that would be fine. Is there a phi square term?
There is no such phi square term.
Then also it's not an arbitrary thing, right? It would be
Just 0. It's fine. Maybe there's some other argument. Somehow, for some reason, this is not dynamic. There are also couplings like this for the dynamic layers, right? So why is this a mass? Firstly, but mass for what?
Which one? This one?
When you say mass, you mean G squared diagonals? When you say give phi away, then it becomes
Right, because this has a mass
meaning
dimension.
G squared, the low energy G squared diagonals.
If there was a gauge group there,
Fine.
maybe there was no gauge group correspond to which this coupled.
And then it would be a mass for what?
For a string, for the little
tension,
string,
say,
tension of the little string.
Fine. Fine. Okay. And so the waves of the other guys would also become tensions of.
Yes, but they will be modulus. You can change them by changing a vacuum.
Right.
sorry. Wave is not modulus. Wave is something that is a super selection sector, right? It's not a
Yeah, I'm just saying it's a wave.
yeah right.
But yeah, by modulus I mean it's a wave.
Okay, sorry. Yeah.
It's some tensor branch moduli.
Okay.
Right. I mean, so this phi corresponds to volume of some P1 in your base in F theory, and this P1 is just frozen. It's just
If f wave star f was 0, suppose you took that equation, say literally, what would that say? That would say that star f was sort of equal to f. Would be a duality or self-duality equation, right?
yes, star F equals to F.
Yes, or minus f or something.
Yes.
So this would then appear to me, if one took Abhijit's point of view literally, this would appear to make that field, that gauge field also non-dynamic.
Right.
That's what you're
No,
saying?
gauge field non-dynamical. No.
Because it would restrict your field configurations to self-dual field configurations, which is basically nothing. No
I mean,
focus.
it's not entirely correct, right? Because this is 4 form, this is a 2 form
Oh.
in 6 dimensions.
Ah.
If star being 0 just says that there is no kinetic energy for that gauge.
No, but let's look at the solutions to that equation. If we were in 4 dimensions, the solutions to that equation would be self-dual field configuration, right? At least one set of solutions.
So dual with that instanton number 0. So it's just
Right.
So there is an intuitive picture, right? You're compactifying type 2b on something, and you just find out that you have the choice of not integrating over phi because there is no kinetic term in the low energy theory. You just start with some configuration, you go to low energies, and whatever fluctuates, fluctuates, right? This thing does not fluctuate. You can choose, this does not interact with anything, you can just say I fix it in the UV somehow. So it depends on how you start in the UV. There is a consistent choice to start in the UV for this to be fixed.
But if you're given a Lagrangian of that type of coupling, I mean that's not what you would do, right? You would just integrate over phi and set that thing to 0.
No, if I'm saying that phi is not being integrated over this, it says somehow in the UV I just set it up such that I don't integrate over phi, This is a self-consistent thing, right?
But why is it not integrated over?
I just start in the UV like that. In the string theory, there is some volume of P1. I am not going to fluctuate it. It's self-consistent in this, with this thing, right?
Why couldn't you do the same for one of the dynamical fields? Just set it to 0 or to set some constant value.
No, but it has a kinetic term.
But you just set it to some kind of constant value, then the kinetic term is 0.
No, so okay. So a priori everything is fluctuating in string theory, right? And then I find out that some field does not have a kinetic term. So I obtain a lot of zero modes. Now I can do a Faddeev-Popov for this, right? I can treat this as I can just remove the zero modes by hand. Just say that I don't integrate over it. I obtain a theory which had zero modes.
Okay.
And then I just say that I divide my measure by this zero mode, by this Rn symmetry. So maybe you won't obtain it directly from string theory, but you can do an operation on it. You can gauge this, the translations of this field phi.
The field, the space-dependent translations.
Yes,
You gauge it.
yes. Gauge this whole field away.
Can't one ask the same question for n equals 4 supernomials on D3 range? The coupling constant is the axion dilaton field, right? Of type 2.
No, that's a wave. The coupling constant is the wave of the axion
Right,
dilaton.
but we don't integrate over it in the 4 dimension.
But sir, you can't gauge that because it couples phi Fh. That's not a gauge symmetry. The shifts, x-dependent shifts of phi,
Right.
change the action because of this coupling. If you could gauge it, then that would be the statement that phi doesn't appear anywhere else in the dimension.
Right.
That would be okay. But the question is, what does it do to these?
And also, I thought that this would, one could think of it as a rigid parameter if it is coming from a sphere that is kind of going off to infinity, like say semi-infinite brane. But this is actually coming from an affine type circle. So all this sphere
Yeah, some compact P1.
which is kind of weird. I mean, I would have expected some rigidity when the sphere is going off to infinity.
I mean,
Boundary sphere.
so if you want to contract this sphere, right, it's at, so from the point of view of Calabi-Yau, there is this compact P1 and I'm saying that its size should be fixed. The reason for saying that is that there is a natural metric on the moduli space of Calabi-Yaus. And in this metric, making this fluctuation of this particular compact P1 is infinite distance away. So that there is no, it's infinite distance. In that, not on the metric on Calabi-Yau, metric on the moduli space of Calabi-Yaus.
Okay.
So this is a mathematical, I mean, this is what is happening from the point of view of Calabi-Yaus.
Let's move on. Yeah.
Okay. 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 Now, in the third case, you assume that MAB is, so this is a positive definite metric. Everything is dynamical. So you expect there are no mass parameters. You expect that you obtain SCFT at the when all the waves are 0. Okay. Right. So the waves of these phi's are just the volumes of these dAs. So waves of phi A. Now you still have to show. So for this, for you to really trust this, you have to show that you started from some generic values of these phi A's.
What will the interpretation of these, the expectation values of phi's be now in this case? That would be like going off on Coulomb branch of the SCFTs?
Yeah, tensor branch.
Yeah.
So the waves are the volumes of the cycles, and if you want to simultaneously take all of them to 0, you want all of the 2 cycles in a manifold to simultaneously contract to 0, and this should happen at a finite distance in the moduli space of Calabi-Yau. Then you have an SCFT. Now this is assured by a theorem of Grauert and Artin, that whenever you have such a base with 2 cycles such that the intersection form is positive definite, you can shrink all DAs simultaneously at a finite distance in the Calabi-Yau moduli space. So the SCFT point exists within this moduli space.
This is always true. That's the theorem.
Yes, for M may be positive.
So far this is just a type 2B picture, right? This is a type 2B picture.
Yeah.
So the elliptic fibration is going to be on top of this.
Yes.
fold.
Yes. So I'm not even talking about any gauge fields right now.
But just before this, when you were talking about spheres and cycles and so
Yes.
on, those somehow came from elliptic fibration.
Those were in the fiber.
So that I shouldn't. This is
You
not-
shouldn't confuse them. Yes. Okay. Right. So now there is a similar theorem analogous to this, which is due to Winberg, which is for M may be greater than or equal to 0. If you have this situation, then there is exactly 1 0 eigenvalue. So this is just a linear algebraic theorem. It has nothing to do with geometry. So if you have a symmetric matrix which is positive semi-definite, it has exactly 1 0 eigenvalue. And the eigenvector, let me call it D, which is some linear combination of these DAs, is such that CAs are all positive definite are greater than or equal to 0.
I'm getting confused with something very elementary.
Yes.
In your simplest example in the first lecture,
Yes.
where you had D6 branes and
Yes. NS5s.
NS5s, the tensor branches were the positions of the NS5s.
Mhm.
And there were as many phi's when you looked at the whole circle as when you
Yes.
looked at it on semi-infinite.
Yes.
So now what is this extra?
This is the addition of all of those phi's.
So that is determined by the other thing.
The radius. As you go around it, you add all of them, you get the radius.
Okay. So the length of that.
Yes.
Fine.
And that was frozen.
Thank you.
Okay. So now since all of these are greater than or equal to 0, you can simply compute the volume of this thing. This will be C given in terms of the volumes of ds, and this particular volume is fixed in our example. So this is the P1 whose volume is fixed.
Can you say again what the Winberg theorem is?
It's just a linear algebraic theorem that if you have a symmetric positive semi-definite matrix, it has exactly 1 0 eigenvalue.
Sorry, I mean, what about 1 0 0? That's a symmetric.
Yeah, so there is a notion of simplicity that it has to be irreducible.
Okay.
The intersection. Right. So yeah. So D3 branes wrapping this P1 will give you the latest string, this D. And you can compute its tension as well. So its tension will be CA volume, the volume of this thing.
But I cannot construct more than one zero eigenvalue?
You can, but it's just that some P1s will be separate from some other P1s, and so you're just constructing a direct sum of little string theories or direct sum of little string theory with SCFTs. Right. So now, in F theory, remember we had three conditions coming from gauge theory analysis. So there was one quantization condition, there was cancellation of gauge anomaly, and vanishing of global gauge anomalies. So the quantization condition was just about the charges of the instanton strings, and we can already see that that it is always satisfied. So we want to compute the charge of a string coming from D3 branes wrapped on the cycle dA, and this will be equal to integral of B4 on dA times on the string world sheet sigma, and this is precisely MAB times B2B on dA, sorry, on sigma. So we see that the Ath string is charged under the Bth tensor multiplet with charge given by the intersection form. And so the quantization condition becomes that MAB should be quantized. Is quantized.
And that's automatic from it being an intersection form.
Yeah, so as long as the base is smooth, this is automatic. It's an intersection thing. So this follows from B is smooth. But if you were to go to the CFT point where you contract all of them, then your base is singular now, and it has fractional intersection numbers and violates this quantization condition, which you don't expect to be true anywhere.
Because the string doesn't exist.
Yeah, there are fractional charges objects. Yeah. So I'm saying that you can go to some non-generic point of tensor branch on tensor branch where you contract some of the P1s. Then the other P1s get fractional intersection number with each other. So the strings at those points of tensor branch are fractionally quantized. Okay, right. So now what were the other conditions? There was a condition about anomaly cancellation. So let me turn to that. Okay, so in type 2B string theory, we have a coupling between a coupling of D7 branes to the gravitation physics. Let me call this coupling as gravitational coupling. Just give it a name. And this coupling is, you start B4 times so here Na is the order of vanishing of delta at the location of the 7 brane, right, and I've already defined other quantities. Okay, and there is a gauge coupling. So there is a coupling of the 7 branes of the bulk to the gauge theory living on the 7 branes. And this is as follows. Here trace is semi-appropriately normalized trace. And this is the field strength valued in the gauge algebra living on the 7 brane. So now you can just combine them, add them, and you obtain a total coupling of B4 to the 7 branes. And you can slightly modify it. You can write so you can write this thing as half C1b, where C1 is the first Chern class of the base. This is the cohomology class dual to the canonical divisor on the base. Okay. Okay. So people know about canonical divisor.
I don't, but if it's not important, you can just.
I mean, it will play a role in the. So this K will play a role in the conditions I will write down, anomaly cancellation conditions. So this is you take your holomorphic cotangent bundle, and you take the maximum antisymmetric power of it. You get a line bundle, and this is the divisor dual to it. It's called the canonical divisor of the base. It's also dual to the first Chern class. Maybe that's a better definition. And this relationship follows from the Calabi-Yau, from the fact that it's Calabi-Yau.
24 is
Hmm?
interesting. 24.
Yeah,
Where does that is
it has to do with 12 and delta.
it? But more geometrically is that?
It's just a fact that Calabi-Yau. I'm using that you are on a Calabi-Yau. You can write this as this. Okay, so now you obtain a coupling of. So you just, if you write B4 in terms of the 6-dimensional fields, you find a Green-Schwarz coupling, and from this you can find the Green-Schwarz anomaly polynomial. And it's going to be a square of
It's exactly what's needed to cancel the anomalies.
yes. Trace R squared. And square of this. So you see that this can be written in terms of the intersection numbers of the divisors which are dual to these classes. So it's written in terms of intersection numbers of Ks and Ds. And you obtain the mixed gauge gravitational anomaly along with the pure gauge anomaly. So the conditions that the type 2B setup has to satisfy is the following. I mean, so in type 2B you will have some geometry, and it will automatically give you a gauge theory. And this is an extra constraint which you need to check for the anomalies, that the anomalies should cancel each other.
Oh, but
It's not a property of.
it's not automatic.
It's not automatic.
So it will constrain the number of kinds of singularities you can have.
Right. So presumably it's automatic. If you do a proper analysis of Calabi-Yau three-folds, elliptic fiber Calabi-Yau three-folds, it should be automatic. But you use instead these anomalies to classify these Calabi-Yau three-folds. This anomaly matching. So these conditions become so I was using the index A there as well. A, sorry.
What's it, EI?
Sorry?
Trace EI.
It's rho I, rho.
What? Sorry.
It's the representation.
But that should also come out, right?
Right, that should be in the data of the fiber, which I have not discussed so far.
Okay.
So this is the condition which must be satisfied. Left hand side is computed from the fiber, right hand side is computed from the base. K is the canonical divisor of the base.
So the first equation should be square, right? Square.
Right, so this is coming from the gauge gravitational, mixed gauge gravitational. I just removed the trace r square. So it's telling you that some combination of the index should be this. Right, and there are mixed things. VAB.
So far the only thing additional that this analysis has brought us compared to field theory is that you knew exactly what the Green-Schwarz polynomial
Is in terms of the base.
is.
Geometry
Otherwise,
base.
it's just, you're writing the same field theory equations that you
Yes,
put with a particular.
yes. And the fiber can be different. So even on the same base, you can have different fibers, as I will describe. So
And
the
that
left
would
hand
be-
side can change.
That's just a black box.
Yes. Okay. Right. So these are the conditions which need to be satisfied to cancel gauge anomaly. And now the global gauge anomaly, it just turns out that it vanishes in all of the consistent F theory configurations. And I don't think anyone has analyzed deeply the reason why that is the case. But why that turns out to be true? Is there if there is any principle behind it?
The term that's like f to the 6, you see. No.
No, the global gauge anomaly about pi 6.
Ah, that.
So there's a sum over ij.
Yeah, sum over ij. So these are like the bifundamentals. Okay. So now I want to move on to the classification of the bases. So first I will classify the bases and then the fibers. Instead of classifying, I will just give you the overview of classification with important points which simplify the classification. So let me first tell you something about some constraints on the base of a consistent F theory geometry. So we notice that if you have points whose order of vanishing for f, so let me write the order of vanishing of fg delta as just simply fg delta. If it is greater than or equal to 4, 6, 12, so we saw examples up to 4, 5, but if you have 4 and 6, then delta is automatically constrained to be 12, greater than or equal to 12. So if fg delta is greater than or equal to 4, 6, 12, these points do not fall in the Kodaira classification. They correspond to non-minimal things. And the interpretation of this is that if you have, suppose you have two, I'm drawing a picture in the base, then I have codimension 1 singular loci, and suppose they intersect at some point, and at this point you obtain order of vanishing greater than or equal to 4, 6, 12.
Sorry, just one
Right.
quick question. Just to get where we're going. You had last lecture worked out, assuming that there was a field theory description, you'd given basically a complete classification of what was allowed.
Right.
Now, I thought what would be new in this discussion is that you would get theories without Lagrangian descriptions.
Right.
But I'm seeing lots of Lagrangian.
So this one is for the ones for the tensors which are coupled to the two gauge fields. For them, you must have anomaly cancellation, and anomaly cancellation conditions are these. If there is no gauge field corresponding to the tensor multiplet, then there is just no condition. And I'm going to classify things without Lagrangian as well.
No, I think the matter fields are going to come from these further decorations with the codimension 1 singularity.
And what about, but could you, I see. So the gauge fields, they will always have, they're always on tensor branches, so you,
Right,
always have
and their
U1
instanton string must always couple to some tensor multiplet.
right, so because we're on the tensor branch, you always have gauge theory description of those guys. They're always like U1s. Is this right? No.
No, I'm just
No.
saying that if you have a gauge field, there must be a corresponding tensor multiplet, because the instanton string has to couple to a tensor multiplet. But you can have tensor multiplets without gauge fields,
Okay.
which are not, there's no correspondence.
So those strings would not be interpreted as instanton.
I don't know.
Yeah, those strings are just strings, not instanton strings. All right. Okay, so you can obtain such points at the intersection of two singularities, and the interpretation of these points is that there are some hidden tensionless strings at these points. You're not completely on the generic point on the tensor branch. So there is a procedure in mathematics literature known as blow up. So you can take a point and replace it by a CP1 of self intersection -1. So suppose you had something like a -m curve intersecting a -n curve, which had this problem, then you can blow this up to get -m -1, -1, and -n -1. If they were intersecting transversely at one point. And since D3 branes can wrap this is obtained as an unresolved situation of this, so there are some tensionless strings over here. Okay, so we want to remove all such points. So we assume that we have done, in our starting geometry, we have done this blow up procedure and reduced to a situation where we do not have such points. Okay.
Blowing up is going on in the base.
In the base.
So, but this possibility that you are mentioning
Right.
is about the degenerations of the fiber.
No, it's everything is in. So
This Fg delta now is some elliptic fiber. Now we
Right,
are starting
right.
to describe elliptic fibration in the base, right?
yes.
So once I have blown up the base so that no complications are there, I could still have this loci.
Then you blow, so every time you blow up, you reduce Fg delta by 4, 6, and 12 on the -1 curve. So the Fg delta on this will be equal to Fg delta minus 4, 6, 12. And the collision of two singularities are never going to produce for you 8, 12, 24. So you don't have to do a blow up twice at the same location. You have to do it maybe at multiple locations until you don't have such points anymore. I mean, this just follows from Kodaira table. You look at Kodaira table,
No,
there,
but I'm just asking simple. So this blow up procedure is for the base,
right?
right? So if I don't elliptically fiber at all,
Yes,
I can do this blow up
yes,
once and for all.
yes.
Now it's done. Now I want to put
No, but
now I
you don't know where you have to do the blow up. The location of the blow up is specified by the points which satisfy this condition. So you need a fiber to know the location of blow ups.
Yeah. So are there isolated points with that kind of order for Fg delta, or do they always occur at intersection of two loci?
They must, right? Because delta is vanishing. These loci are just the places where delta is vanishing, by definition.
Oh, okay.
There's some 2 cycles in a manifold.
Right, but you're saying that delta can be greater than equal to 12 only at the intersection of two such loci.
Yeah, so I start from things which are in Kodaira's list. They do not, they are
Oh, they don't
well behaved. Yes,
Which means you have to enhance it to
you need an intersection. Yes. Right, so here there's, right, so as Abhijit is pointing out, there is some interplay between base and fiber, which we do not understand very properly. We're just saying that if the fiber has this, then you should enhance the base, you should introduce a new tensor multiplet. Okay. So we assume that this procedure has been done, and now we combine the fact that we have restricted our base and we combine it with MAB being positive, we obtain some constraints on the base. And these constraints were obtained in a paper by Heckman, Morris, and Waffa. So the first constraint is that the genus of every DA must be equal to 0. So they must be P1s. They cannot be any torus or higher genus surfaces, higher genus 2 cycles. The second constraint is that dA.dB must be either 0 or 1 for all A not equal to B. So you cannot have two curves intersecting at 2 points. And the third is that you don't have any loops in the full diagram. So you don't have things like this. You must just have trees.
There's this deaffinization you're going from LSTs to SCFTs.
Right, so I will turn now to the constraints for LSTs, a similar table for LSTs, and then some kinds of loops will be allowed. So let me write down the table, and these constraints were worked on in my paper with Del Zotto, Heckman, Morrison, Rudelius, and Waffa. So in this case,
Conditions follow just from that MAB greater than 0, these conditions.
no, greater than 0 along with this restriction that there are no such points.
So the Friedman classification doesn't enter here at all.
Which Friedman classifier?
Friedman's classification of 4 manifolds.
I don't know about it. I don't think it enters. It's just simple. It's an algebraic geometric classification. It does not care about differential geometry,
No, just
topology or topology.
This is topological. I mean, the most basic structure that is ever possible, right? Just topology. There he says.
No, this is algebraic geometry, so it's even lower.
No, it's much higher.
Okay, these are just some equations. I'm solving some equations, algebraic equations. Okay, in this case, you have. You can have genus equal to 0 or 1. Now, if the genus is 1, if you have a torus, then it must be that it is isolated. That is, dA.dB must be 0 for all B not equal to A. So this is a theory by itself. Why is this the case? Suppose you had a situation like you had a torus, and you had a P1 intersecting it, let's say. Then I can just, this is on the tensor branch, right? I can take the tensor branch modulus for this P1 to be infinity, and I will obtain this configuration. And we know that there is, from the theorem of Windberg, we know that there is only one little string. There was only one possible 0 eigenvalue. So this little string theory must flow to an SCFT. So that means that this theory must be an SCFT. But from this result, we know that this is a contradiction. Right. So this means that a torus can only appear in isolation. So this is something. This is sort of a tensor decoupling. You're just decoupling a tensor. This argument can be, and under tensor decoupling, little string theory should flow to superconformal field theories. Using this argument, you can just take the SCFT classification and convert it into little string theory classification. Basically, that was the point of our paper. Okay, and similarly for the second one, you can have dA.dB equal to 0, 1, or 2. And if you have a dA.dB equal to 2, again from tensor decoupling, there are only a finite number of cases which are possible. So they are basically a -2 curve intersecting a -2 curve. So by this I mean 2 intersection points, a -4 intersecting in 2 points at -1, or these curves can intersect tangentially, which will count as an intersection of order 2. So they can intersect something like this. By this I mean tangential intersection. So these are the only allowed possibilities when dA dot dV is 2. Okay, and for the third one, for the loops are allowed. But once you have a loop, the loop cannot have any branches by tensor decoupling. So the only loop which is possible is of the following, is like a necklace. No branches possible.
Now, each of these P1s is associated with one gauge group. Is this right? Because each
Yes,
of these,
no, not with gauge group, with one tensor multiplet.
and therefore with one gauge group.
No,
I
The-
thought each tensor multiplet came with a B mu nu, and the B mu nu coupled with the instantaneous or something.
no. So if you have a gauge group, that must couple to a tensor multiplet, but not the other way around. For example, 2,0 theory, that has no gauge multiplets, but a tensor multiplet.
Without anything charged under the gauge, under the B mu nu, you're saying.
Yeah, I'm saying.
Without anything dynamic. No. Sorry, you're saying that you could have a tensor multiplet and therefore a B mu nu with nothing charged under the B mu nu?
There will be a string charged under B mu nu, but it won't be the instanton string of a gauge theory. Okay, so now using these constraints, you can classify the bases.
So is this the point that one of the gauge group, one of the quote unquote gauge groups becomes like a flavor symmetric?
Becomes a flavor? No.
I mean, suppose you were in the SCFT kind of thing.
Right.
No, it's the other way around. Sorry.
Okay, so to classify the bases, the strategy that was used in a paper of Hackman, Morrison, Rodriguez, and Waffa was that you first classify the maximally Higgs configurations. So
sorry, in a situation like this, we still don't know how many gauge fields there are going to be.
we still don't know.
Okay.
So I will talk about gauge fields now, starting now. Okay, so we are imagining we have some sort of theory, and we are just Higgsing it as much as possible. Now, is it possible to completely Higgs it in 6 dimensions? Answer according to F theory is that no. There are sometimes some clusters which cannot be Higgsed away. So there will be some gauge fields and some matter left, such that you just cannot Higgs it away. Higgs the gauge group completely away. Okay.
So when you're saying Higgsing, you're saying on tensor branches. The tensor kind of
On the tensor branch, everything is happening on tensor branch in the classification. Okay, right. So how does this constraint follow, right? So there is a table for these. Let me present to you the answer for these non-Higgsable clusters. These are called non-Higgsable clusters, and there is a finite table for them. So you can have. There are more complicated cases, but let me just.
Just to make sure I understand, non-Higgsable meaning you cannot move the NS5 branes away, so to speak. That
You cannot.
Not Higgsing the D6 brane theory.
I'm talking about Higgsing the D6 brane theory. The gauge Higgsing the gauge group.
Okay, so I
The standard way of Higgsing.
But we still have not understood where the gauge field comes from.
It's coming from fiber, and I have not talked about fiber at all. Right now I was just constraining the base.
Sorry, but didn't you tell us, maybe I forgot, but didn't you tell us right with the analysis of supersymmetry that it was not possible to Higgs? There was no such thing as a Coulomb branch for.
Right, but there is a Higgs
but
branch.
There's a Higgs branch, thank you.
Yeah. Okay.
So it's like a matter getting a wave.
Yes. Okay, so for these non-Higgsable clusters come in three kind. They can either have single 1, 2, or 3 intersecting P1s.
So these telling us about what cannot be Higgs is roughly telling us about the nature of matter. Nature of the matter interacting with the gauge fields.
Mm-hmm.
I'm asking. So this is some constraining what kind of matter interacts with the gauge fields.
Right, so these will be, I will give you some gauge group and some matter charged under it, which cannot be Higgsed away. Okay.
In your Lagrange classification, you saw this also. Is it easy to see this non-Higgsable clusters
I mean, so yes. I mean, it's just some matter. Sorry.
If you have bifundamental matter, then the center of mass U1 cannot be.
So one example of this is that you have E7 gauge group with a hyper transforming in half hyper transforming in the 56 dimensional representation of E7. Okay, and so this is one example of a non-Higgsable cluster. Why can't we Higgs it from the point of view of field theory?
Why can't you?
I mean, do you see any problem?
Well, so suppose you give this thing a wave,
Right.
and you ask how much of E7 commutes with it. I would have thought that that would be the non-Higgsable part. The part that commutes with a wave of this.
Yeah.
But are you saying all of E7 is non-Higgsable?
Yeah. So this thing is not Higgsable anymore.
Why not? Why can't you give that thing a wave?
I mean, it's just
I mean,
no. It's just not possible.
what does that mean?
It's a geometric constraint, so the geometry won't make sense if you Higgs it away.
But in field theory, can you say that?
No. Yeah, so I don't have a good field theory understanding why this cannot be done.
Is this the simplest example? There is an example with some SU2, SU3 or something like that.
Yeah, but they don't have matter.
You don't think those are physics dimensionally?
No,
Physics is simply What's wrong with you?
there is a better example. So you have SU2, SO7, and SU2. And then there is a half hyper with the spinner here. So you have a half fundamental and a spinner, a half spinner and a fundamental. This one cannot be Higgs as well.
Say that again. Sorry.
So this is SU2, SO7, SU2 gauge theory with matter transforming in the half hyper of fundamental tensor spinner and half hyper of spinner tensor fundamental.
Again, it looks like it could be almost completely mixed.
Yeah, one should perhaps write this BPS equation. So the Higgs branch is not there. That's the statement.
On the tensor branch, there is no Higgs branch. There is no intersection of tensor branch and the Higgs branch of this theory, of this.
Oh, once
Gauge
you
theory.
move off in this direction, you cannot move.
You
on.
cannot give away.
But that one should be able to see that from just the BPS equations, right? I don't know how.
Which BPS equations?
Of the modulus space. For these theories.
Yeah, but you don't have a Lagrangian, right? If you mean the Lagrange?
I thought this is the Lagrangian, no?
Yeah, but then you can certainly Higgs this gauge theory, right? From the point of view of Lagrangian.
I thought that you were saying we cannot.
You cannot Higgs the 60 theory. The 60 theory does not have a Higgs branch going from.
Yeah, 60.
It's just that this theory has a Higgs branch, but it is not the part of the Higgs branch of 60 theory. I think that's what the statement is.
If this theory
If you try to Higgs it, you have to leave 6-dimensional theory.
6 dimensional.
It's not a vacuum of 6-dimensional theory. Of the super conformal field theory sitting on top. Otherwise, I think you can just Higgs it, right?
You are saying the Higgsing somehow doesn't commute to it.
Does
going
not
to
come.
the tensor branch.
Yes,
Something like that.
yes.
So even if I can Higgs this particular theory, that doesn't mean that the SCFT associated with it,
Yeah.
I can directly move in this direction
Yes.
there.
Yes. So the Higgs branch of SCFT is more yeah. There is no vacuum corresponding to the Higgsing of this gauge theory. Okay, so now let me show you geometrically how these things arise, why these constraints arise. Let me first write down so these are only possible when you have either 1, 2 or 3 number of intersecting P1s. And for the case of one intersecting P1, let me write down a list. So you can have a -3 curve, a -4, -5, 6. Yeah, you can have up to 8, -12. And the gauge, there is some non-hixable gauge theory which must survive on them, which is this one. 7. And for this, you also have a half hyper in the 56-dimensional representation. And for the others, there is no matter content. So let's see why, if you have a -3 curve, you must at least have an SU3 on top of it. So for this, we will use two geometric facts. The first is called adjunction. It states that if you have any curve sigma in your theory, then k plus sigma dot sigma in your base, it must be 2g minus 2. And so in our situation, it will be -2 for these things. Sigma dot sigma is -3. So this tells you that k dot sigma is 1. And I did not tell you this. So this was some important information that I should have told you. F is a section of -4k, G is a section of -6k, and delta is a section of -12k. Okay, so we can see what is the intersection number with -4k, -6k, and -12k for sigma. So for -nk, this is going to be -n. And there is this fact that whenever minus nk dot sigma is negative, then you can write minus nk as sigma plus a divisor x, such you can write it in this fashion. Okay, and this is true for any some special divisors which are called effective divisors, and minus nk is one of them, and x also has to be is then effective. So you can use this and so on, right? So you can see what is the intersection of x with sigma. So let's do it for 4. So you have -4k dot sigma is -4 equal to -3 plus x dot sigma, and you obtain that x dot sigma is -1. So you can go one step further. You can write this as 2 sigma plus x now, and now this one is positive. So you truncate when you have something positive. And what this is telling you is that, so this was for -4k, for -6k you will obtain 2 sigma plus x again, and for -12k you will obtain 4 sigma, 4 sigma plus x in this special example. So what this is telling you is that these divisors are comprised of some parts of sigma plus some divisor which intersects it at some points, because positive intersection has to do with the counting number of points of intersection. So this means that that -4k vanishes at sigma up to order 2, at least 2. -6k vanishes at sigma up to order at least 2, because these right, if you look at divisor, you look at the vanishing of these line bundles, and -12k vanishes at sigma up to order 4. So you obtain order of vanishing of fg delta greater than equal to 2 to 4. And if you go to Kodaira's list, I think this is Kodaira singularity of type 3, which has an SU3. So this one 2 to 4 is type 3, and which has at least SU3 on it. Type 3 carries SU3. And similarly for other ones, the matter can be read off from geometry.
Sorry, I'm beginning to lose you. You're trying to classify these non-higgsable clusters, is this right? Yeah.
Yes.
And what is the principle you're using? How do you know when something's higgsable and not?
So I took an example to illustrate that. I took an example in which I have a single curve in the base, which has self-intersection -3. And then using geometry, I showed that f, g, and delta must vanish on this divisor up to at least order 2 to 4. And if you go to Kodaira's list now, order 2 to 4 corresponds to type 3 singularity, which carries a gauge group SU3. And if you have higher singularity, the gauge group was also higher. This is a fact about Kodaira's list. So you have at least SU3 there.
This non-exhibleness was, and the correspondence of that to 1 to 3 intersecting P1s was, how did that come about? That was in
No, that is just, I'm just telling you a result that these only happen for 1, 2, and 3. And for 1, this is the full list. For 2 and 3, I'm not writing it down.
Okay, but there is a finite list.
Yeah, there are only 2 or 3 more cases. Okay. In particular, the SU2, SO7, SU2 came out of 3 from this 3 intersecting P1s. Okay. Right. Okay, so these are the non-accessible clusters. So these are the building blocks for my base. And we see that a particular base must carry some minimal amount of gauge theory on it. You cannot completely Higgs a base. Okay. Along with this, you can also have -2 curves intersecting in the fashion of a finite or affine AD Dinkin diagram. So finite for the SCFT case, affine for the little string theory case.
In this language, have we already gone to the tensor branch?
Right, we are just talking about tensor branch.
So now you're
Throughout
talking about
this.
whether this tensor branch is Higgsable or not.
Yes.
Isn't that different from what we discussed before?
Yeah, so that's what I was saying. I was saying that the gauge theory on the tensor branch can be Higged, but this new vacuum is not a vacuum of the SCFT. So for example, this one, right? This one can be Higged.
Right.
The gauge theory can be Higged. Naively, you will think that there is a vacuum of the SCFT corresponding to the Higged one, but F theory is suggesting it's not possible.
But what I haven't understood is how this analysis is telling you about the original untensored theory. Because it seems to me that you're just working on the tensor branch
Yes,
and you're getting some statement about singularities on the tensor branch.
right.
And therefore you're saying that you cannot Higgs even on the tensor branch.
I'm just saying you cannot Higgs on the tensor branch. I'm not saying anything about the SCFT point.
Yes, but doesn't that contradict the fact that we know you can Higgs in the gauge theory?
Yes, and so the point is that there is some sort of UV physics governing, is removing this Higgs directions. There is some physics which we do not understand from the point of view of low energies, which is lifting this
And this
directions
this
away.
statement we can make purely sitting on the tensor branch, because your geometrical analysis is only telling you about tensor branch, right?
Right. But it's coming from F theory, so there might this F theory things might know about some other things, right? The F theory is a very constrained setup. The SCFT also lives inside F theory. So you're using some tool to get this. You don't really know from the point of view of low energy what is actually happening, what this tool is telling you. The tool is telling you that this is the truth. But it's not telling you that it's following completely from low energy physics. It might have high energy data in it.
Okay.
There's no separation of low and high energy data.
But just to repeat again, even on tensor branch, once you've gone to the tensor branch, you still cannot Higgs. That's what you're concluding.
Yes.
And you're saying from low energy point of view, it's a mystery why you cannot.
Yes. Or maybe the mystery has been resolved. I just don't know the answer.
Yeah.
Okay. So along with these ingredients, you can have -2 curves intersecting in a finite affine fashion, ADE fashion. These are just the 2,0 SCFTs or 2,0 little string theories. They do not carry any, so the fiber is completely trivial. So fiber is just a T2, non-degenerate T2 over these things. Okay, and you know the fiber over them as well. And the final ingredient is something called the E string theory, which lives on a -1 curve. The fiber is again T2.
So, just one question. Going back to something Abhijit said earlier, if you wrote down the D-term contribution to the potential in these gauge theories,
Mm-hmm.
are you sure that one can Higgs consistent with setting that to 0? In just a low energy gauge. There's no F term here because there's no superpotential. But are we sure that the D-term condition can be satisfied? Maybe could it be just as simple as that? Or is that
It's weird. It somehow holds only for these things. SU4 is okay, for example.
Ah, it sounds okay. Yeah, doesn't sound like.
Are you saying this also the adjoint? No, what is the scalar that you will Higgs SU3 with?
Mm-hmm.
What is the scalar that you will use to Higgs SU3?
That's also confusing.
Vector multiplier does not contain any scalar. So there is no scalar, that is okay. SU3 is okay. It's only this one which has a problem.
So from all this analysis, you concluded that pure SU3 without any chirals cannot be gauged. That's what you concluded?
No, I'm just saying that if you have a -3 curve, you must have SU3 on top of it.
No, gauge theoretically.
Gauge theoretically is just an SU3, which could anyway not have been gauged.
Which anyway cannot be gauged.
Cannot be gauged. So is this -7 one which is the real thing? There's something non-trivial there.
SU4 not in the list, for example. Why is F3 not telling you that SO4 without matter, SU4 without matter cannot be gauged? Because that's also a trivial conclusion.
I mean, if you could realize it, then yes. I mean, you could realize it. So, no, SU4 with -2 can be so SU4 can be realized on -2 with I3 SU4 singularity on it, and you can gauge it to 2, 0.
Okay, so what happens if you try to do this for SU4 and gauge it and Higgs it? What does that mean?
So what is the matter here?
It's an SU4 theory.
And the matter is?
Then no matter. Oh, so you need a matter, right? So that's the point. For SU3, you do not need a matter. It's consistent to not have matter. For SU4, you must have matter. As you must have a 8 hypers in the fundamental, at least. This has to do with the fact that for SU3, trace f to the 4 does not exist. And it's always quadratic, so it's always consistent.
In other words, these are just listing pure gauge theories.
However, that E7 has some matter.
Right.
Okay?
Yes.
But suppose you had U1 with just one charged field, then you couldn't Higgs it.
Okay.
Because the D-term condition is sum over EI phi I.
Right.
So maybe that E7 is like that.
It's like that, yeah.
Hmm.
Even the gauge theory, the Higgs is not.
Right.
So I guess, yeah, so the analysis whether one can gauge it or not is kind of straightforward, but just the existence of the theory
Is not so.
is not so obvious.
It's
and that is-
limited.
Yeah, this is probably telling us about that.
Okay.
Actually, I'm going to have to go in 5 minutes.
Okay.
You guys can continue. Yeah. So maybe in 5 minutes we can try
Okay.
to, I mean, just go to a natural topic further.
Okay.
We could continue later.
So there's a talk scheduled on next Wednesday.
We should talk to Anshuman, I don't know.
Yeah, I think Anshuman. He told me some way.
Right. So I don't have much things left to say.
Good.
This will probably take 7 or 8 minutes anyway.
Good.
Okay. Right. So I was telling you what are the ingredients to build a base. So first of them is the non-Higgsable cluster. Second are these -2 curves intersecting in a finite or a fine AD fashion. These are, what are the theories corresponding to these. These are the 2, 0 SCFTs or little string theories. The fiber is trivial over this. Final ingredient is something called E string theory, which is over a -1 curve. And this has the property that it has E8 flavor symmetry. So another construction for this theory is on the end of the world. So you start with an M9 brane. M9 brane carries E8 flavor symmetry. In M theory, this is M9, and you put an M5 nearby. The distance between M9 and M5 is the tensor branch modulus. This is the volume of the -1 curve. And SCFT is obtained when M5 hits M9. So this is the E string theory. It contains this E8 flavor symmetry. Okay, and the second wall is sent to infinity. Okay, right, and then there are some rules to combine them to get any arbitrary base. So because this has E8 flavor symmetry, you can just combine these non-excitable clusters and -2 curves around a -1 curve, right? Some of these clusters or -2 curves, such that the things which touch the adjacent neighboring curves must have a gauge symmetry, must have a symmetry which is a subgroup of E8. Okay, and another condition follows from the fact that okay. Okay, so in this way you take these building blocks and you glue them using -1 curves, making sure that you satisfy the condition that the groups must live inside E8. This produces for you an arbitrary base. This gives you the classification for the bases, and now you obtain a base with some gauge theories scattered around somewhere. Wherever you have -2 curves or -1 curve, there won't be any gauge group corresponding to it. So these are the example of tensor multiplets which do not have a gauge theory counterpart. And there are some other such examples among these cases.
So these are building blocks because this is the smallest thing you can get after heat sinking things.
Right.
That's the idea.
Right.
In your simple example in the first day with the D6 branes, there were as many gauge groups as there were tensor multiplets.
Right. So those have not been produced right now. I just classified the maximally hexed bases.
Right.
So now we need to unhex them. So unhexing them corresponds to tuning your singularities and making those singularities more singular in the elliptic fiber. So how do you do that? In general, it's a very hard problem, but you can use the anomaly cancellation analysis that we had. So you tune them such that your anomaly cancellation conditions that I wrote down are satisfied. So combining these two ingredients, you can now classify all of the theories. This is the strategy of the classification. Right. Finally, and you can do the same for later string theories. I wanted to make some comments about T-duality of later string theories in 2 minutes. So how does T-duality operate? We don't have a full understanding of T-duality right now of all
So
the.
one quick question before you. On the tens, the non-Lagrangian part, the things that cannot be built out of Lagrangians are non-Lagrangian because the analog of the matter is non-Lagrangian?
Right.
And you've told us how you get such things?
Yes, there were these -2 curves and -1 curve,
Okay.
which did not have a gauge theory corresponding to them.
Those were, I see, thank you.
Okay. So right. So how does T-duality operate in this theory, right? So let me focus on one example. So one example that we saw a few days ago was that you can take D6
I
branes.
don't know anything about these so these things are charged under these non-Lagrangian things. Are they charged under various gauge groups that appear in the model?
No.
So they're just there on their own.
Yes.
How are they interacting with anything else?
So the strings are interacting with the instanton strings. They are charged under the tensor multiplets. So you can have things like this, right? So you can have -1, -2 with some gauge group on it, let's say SUK or something. Then this -1 guy is interacting with the tensor, is charged under the tensor multiplet corresponding to this curve because of the intersection. Okay, so one example of later string theory that we saw a few days ago was this having D6 brains and D6s and K NS5s.
So luckily, I'm sorry to slow you down, even though
Yeah.
we're the ones in a hurry. But in Guyotto's story, you had these sort of non-Lagrangian theories which had some flavor symmetries, and then you could gauge some of those flavor symmetries.
Uh-huh.
So you could think of, in that story, you could think of the non-Lagrangian stuff as the analog, as more complicated matter, which you then gauged.
Yes.
Is there any analog of that situation?
All of the 1, 0 SCFTs.
Uh-huh.
Because we are just describing the tensor branch, right?
Yes.
But if we go to the originate, they are just some SCFTs. They are non-Lagrangian SCFTs.
Right. No, but I mean these curves, -1, whatever.
Right.
Can I think of them as
The tensor branch of a strongly
something
coupled.
that is gauged in some way, that is coupling by a global symmetry being gauged with respect to a Lagrangian component?
Yeah, we did some of those things, right? So we started with this E-string theory. This is a strongly coupled CFT. It's like the example of this Argyris-Seiberg CFT in Gayatto's paper.
Yes.
So it's a strongly coupled SCFT, and it has a tensor branch on which this becomes this -1 curve. Okay. We can take some. So now this has E8 flavor symmetry. This has a property that has E8 flavor symmetry. So you can bring in some components which live inside E8 to gauge this E8. So you can have this E string, and you can put one of those things, right? Let's say -3 curve, and this is the tensor branch of some other SCFT, right? SU3. You can put this thing there.
And the anomalies would work out. That's some more guarantee.
Anomaly for SU3, yeah, it will automatically work out. So this is one example of what you were talking about. This has been crucially used in the classification of bases. You are bringing in things to inside it. Does that answer the question?
Yes, I think
Okay. Okay, so one example of a little string theory we saw was with n d6s wrapped on a circle and k ns5s. This has a T dual in which you just interchange n and k. So nk goes to kn. You see it by if you first compactify it on a circle, you do a T duality and you get a PQ web of D6 and D5 and S5 brains. You do an S duality to interchange K and N, and do a T duality back to obtain a theory in which K and N have been interchanged. Okay. So how do we see this T duality in the F theory setting? So in F theory, this is realized as some -2 curves in a loop. Number of -2 curves is k. So there are k -2 curves, and the fiber over it, which is describing the SU1 gauge group, is this IN fiber. And remember that, so this IN fiber is unresolved right now. So it's something like this. Right. Okay. So now we put this theory on a circle. Once we put it on a circle, we obtain an M theory configuration. So we obtain M theory on the same thing. And now we can resolve this. When we resolve this, we obtain again in the fiber we obtain these things. But now there are n number of these -2. They are also -2 curves in the fiber, and there are n number of these -2 curves. So from the point of view of M theory, you can either view this as IN fibration over an IK base, or the other way around. And you have a circle in the game, so you just go back to F theory to interchange K and N. So these sort of arguments work for more examples than this, but if you want to describe T duality of a general little string theory that has not been worked out yet, what are the T duals of various little string theories? because this becomes a very harder and harder geometric problem. You have to see, in M theory, you have to see whether there are more ways to view this as an elliptic fibration, more than one ways.
Sorry, can you say the last statement again?
You want to find out in M theory if there are more ways to view the whole manifold as an elliptic fibration. And this is a very hard problem to solve. It's not just some algebraic geometry. Right, so
That's why you cannot classify what?
you cannot find out what are all the T dual pairs.
Okay.
We have a list of later string theories, but we don't know which ones are T dual to which ones.
And for SCFTs,
You don't have a,
this T duality cannot be there if this circle is non-compact.
there is no notion of T duality for SCFT, right? T duality is something which is a property of later string theories. And from the point of view of geometry, your base won't be a loop, right, in this example. So you won't obtain another fibration when you go down to M theory. You need this to be a loop, because the fiber is a loop. So T duality becomes a fiber-based duality in F theory, in some sense.
But suppose I didn't have that circle there. I mean, this was just infinite.
Right, in the SCFT situation.
You have the SCFT situation. Now, just in string theory, I
Right.
take another circle, I T-dualize on that circle, so
Yes.
I get D5s, NS5s.
Right,
Then I S-dualize, that will become NS5s, D5s.
right.
And now I T-dualize again. What stops me from doing that?
No, so in this situation, you T dualize back on a different circles,
That's
right?
the point, I see.
So back on this circle.
Yeah, you T-realize back on because now you want it once again to become D6s.
Right,
But
So
it's those guys that have now become the D6s. So
Right.
you need to go on that.
yes.